Welcome to this presentation by AGS India. As a part of the Design Validation series of presentations, we are pleased to bring you a new topic of presentation titled How to Ensure That Your Designs Work. We hope you enjoy this presentation. The agenda of today's presentation starts with a look at the current scenario and the analysis of the same. Design process, the way it should be holistically represented, comes next. Taking cue from the design process, validating a design, why it's required and when it is required is analyzed subsequently. Ensuring a working design comes of use, how to go about doing it for different kinds of verticals and applications comes next, summarized by the benefits towards the end of the presentation. Where do we stand today? Design teams are always facing challenges and problems, either due to product recall because it's not meeting the customer specification, rework due to performance issues, testing not going well, the product getting tested at the supplier's place, at the customer's place, or at our own facility, leading to failures, unintended failures that we did not foresee in the first place, are not being acceptable in terms of durability, in terms of performance. All these leading to challenges coming back to the design department to look at it back on the drawing board. The common denominator for all of these issues that happen in any organization day in and day out are time overruns, cost overruns, and on top of it, image issues, especially if there's a product recall from the customer. Unless we sort this out at the design stage, the problems are simply not going to go away. The design process. Let us take a look at the design process. If qualitative issues are going to be a challenge subsequently after the drawing has been released, why not look at it as the initiator of the design process itself? That's why the DFQ objectives are put as the primary source of information or primary objectives that we need to start with when we start going about initiating a design process for a product or a process. The assembly objectives and the performance objectives are the classifications that the DFQ take. The assembly objectives lead to the design for assembly, leading to the datum reference frames, back to the GD&T drawings if GD&T is used, or simply to the plus or minus tolerance drawings. The DFMEA forms the heart of the whole process. DFMEA stands for the Design Failure Modes and Effects Analysis. The risk priority number specified in the DFMEA against potential failure modes classify the objectives as critical, essential, and desirable. The performance objectives are driven by DFMEA, and the DFMEA gets influenced by the performance objectives. The DFMEA is a driver for the assembly objectives in terms of the risk priority numbers. The DFM, which is nothing but the design for manufacture, design for cost, design for life, which comes from the performance objectives, design for performance, design for transportation, design for service, and any other DFX, could be ergonomics, could be safety, or any of the other considerations. These together in sum total forms the design process that we need to take forward, initiated from the DFQ all the way to the drawing release. Validating a design, why and when? Why should we validate a design? The benefits of validating a design are: it increases the design confidence, it improves the product reliability in a quantifiable manner, it eliminates errors that could have crept in as a part of the design considerations that could prove to be costly, it reduces the input cost, specifically in terms of the number of parts going together, the materials used. Optimization comes in, as a result of which reduced input cost becomes a reality. Then it assures superior performance, enhances the product quality, and protects the product safety. These points, when taken together, have implications on the commercial side. Benefits are many on the commercial side. Benefits on the legal side are as well there. Social and moral benefits come in together. Together, this forms a complete business case as to why design validation needs to be done up front. When we write an email, we do a spell check. When we write a report, we do a grammar and a syntax check. When we do a design, it's necessary that we do a spell check called design validation. In other words, design validation is the spell check for any design. When to validate a design? If the cost of the product is important, increased profitability is a must, enhanced warranty is a threat, improved reliability is a mandatory requirement, green design is in focus to protect the environment, or from a corporate social responsibility point of view, customer satisfaction is required, the product development cycle time should be reduced so that the time to market can be shorter and faster. Then in all these cases, if the objectives are crystallized among these classifications, then design validation is important. We all know that the design is only as strong as its weakest link. We need to know that weakest link as a part of the design process where validation becomes intrinsic to understand this. What are the design validation objectives? The design validation objectives critically have to be aligned with the critical business issues of the organization. If the design validation objectives are not in alignment with the critical business issues of the organization suffers. So, design validation objectives could be sizing, could be driven by weight, could be driven by cost, could have safety as paramount importance, could be a performance requirement in terms of deflections, stresses, vibrations, efficiency, and so on. It could be a life requirement in terms of warranty. It could be qualitative in terms of the quality of the product. It could be sustainability. These are some of the objectives that we look at specifically with the manufacturing enterprises of today. Let's look at some examples. Here is a machine design drawing. Machine design validation is very important, as we can see from the questions that we ask ourselves. This drawing that is shown over here from SolidWorks needs design validation before it is released out. Will the shaft break? Or any shaft break in this assembly? What is the life expectancy of this system? We all talk about factor of safety. How is factor of safety related to the life of the product? Because at the end of the day, to the customers, we are providing warranty in terms of number of months or years, and not in terms of factor of safety. Can I meet the weight target with regard to this? Because transportation and shipment of this is going to be an issue. Will power consumption be more, or would it become my unique selling point in terms of efficiency? Would anything break under the warranty? This is always an issue with every organization because extended warranty is now becoming the norm. If I were to reduce 10% of the product cost, where would I start? You have to start in design. Validating a design at every step of the way helps us to reduce cost. Will I get vibration and noise? Upfront validation eliminates this issue so that downstream problems do not occur as a result of this. Because fixing a problem after the tool has been prototyped, or after the tool has been put together, or the prototype has been put together, it requires surgical intervention, which is always painful. Not to speak of the cost and the time overruns. Why should finally the customer buy my product as compared to the competitors? Simple things like this. If you look at the presentation slide on the left side, the machine design, it's actually a special purpose machine design. If I were to reduce the number of bearings, or the size of the bearings, or the type of the bearings, so that the overall cost of the bearings comes down, this has to come from design validation. Imagine if this cost savings is going to happen in one special purpose machine. How about the same affecting for 10 machines to be supplied to the end customer? The savings are monumental. So it's good that we start with the design so that the design can be validated as a part of the process so that least cost designs become a reality. Powertrain design validation. On the left side, you are seeing a gearing assembly with the end cover for one of the castings where the gears come in place with their shafts. Will my gearing wear out? Will there be vibrations and noise during operation? If we are developing a prototype and we are putting things together and we are testing it out, the first thing that we do is to check the vibrations at the bearing locations or the bearing mounts. Why can't we do that as a part of the design validation process even before the first drawing has been brought out? That way, the vibration and the noise problems can be eliminated up front. Does the casting really need a wall thickness of 22 millimeters, or can it be reduced to 15 or 20? Every millimeter that is saved over there saves the weight of the component. Can heat generation be kept under control? Can I select lower size bearings without compromise on performance? This is what we talked about earlier. What is the abusive load that the system can handle? Can I make this product robust and at the same time look sleek? These are considerations that the design needs to look at as a part of the powertrain validation shown over here. All these are done inside SolidWorks using SolidWorks simulation. Anti-vibration mounts, design validation. Engine mounts, compressor mounts, so many different mounts are used in vehicles, in power systems, in power and process industries, in machine designs, in so many different areas. Can the mount meet the required dynamic characteristics? Will the mount meet the NVH targets? How does the product compare to competitive products already in the marketplace? Will the mount meet the triaxial durability targets? How to achieve the cost targets? Will the design meet the life expectancy that is required? Can alternate material be used in these cases? These are all questions that we need to answer before the sign-off happens on these mounts. Again here, SolidWorks simulation, the advanced dynamics concepts of it, comes up with the point mobility estimation, leading to better designs, eliminating the teething problems that come with the noise, vibration, and harshness, leading to a better performance. Equipment design validation. Will my equipment be able to pass the hydro test? On the left side, you have a picture of a complete equipment wherein there is a cylindrical structure and a rectangular structure duct gets attached to the cylindrical structure. If we look at the ASME code, the code is silent about these kinds of transitions. Closed form solutions are unavailable for these kinds of designs. We develop these designs and put it together and do a hydro testing subsequently down the line. And if the components fail, how do we go about fixing it? How do we know what caused the failure? What would happen if there were to be an earthquake? Can I get the pressure and velocity profiles for air efficiency? We are looking at a cyclone at the bottom, which is used specifically in electrostatic precipitator circuits to take out the fly ash as a part of the pollution norms. How to go about estimating the cyclone's efficiency so that the Environmental Protection Agency's regulatory norms can be met with, can be complied with, or can be exceeded. If you exceed it, it becomes a unique selling point for your product. Can I eliminate the shaft breakages as we asked earlier? Will my design meet the ASME code FEA requirements? Because the appendix of the ASME code, Section 8, Division 2 on the pressure vessels is now becoming as large as the main design document itself. Can I achieve the weight targets without compromising on the safety? Can I use alternate materials, cheaper materials, exotic materials for lower weight? So many different considerations are there. Can I find out the load distribution? Because simplified representations are no longer valid for continuous systems of these kinds. You open the valve. Once you open the valve, the pipe vibrations come in. How are those pipe vibrations, the pulses, going to affect the piping circuits? These are all things that need to be understood upfront even before the drawings have been signed off. System design validation. Will my system withstand burst pressure test as shown on the left side? Can I reduce my BOM, the bill of materials, or the bill of quantities so that my overall cost comes down? Are my pipe sizing and support adequate? We have had situations where titanium pipes are being used in slurry conditions and the pipes start vibrating and at any time they could break, leading to plant shutdowns. These need to be eliminated upfront. What are the possible failure modes I can expect? Is it possible to use a smaller pump for a lower power consumption? Small things are beautiful, right? Where are the performance bottlenecks? Is my design safe? In all these reliability considerations, system design validation becomes a must. Machine tool design validation. This is another example. Customers are looking at high-speed machine tools these days. Earlier it used to be 5,000, 6,000 RPM. Now people are looking at 13,000, 18,000 RPM. Cycle times for these machine tools are getting reduced. Can the tool vibrations be eliminated? Can I increase the tool life? Is it possible to reduce the tool changeover time? Design for assembly comes in along with the design validation process here. Frequent failures of tools, can they be prevented? Can deflections be maintained within specific limits so that the performance of the tool itself is good and acceptable consistently? Can all the forces be eliminated upfront? These are questions, the answers for which are being sought upon by the design engineers as a part of the design validation process. Material handling equipment design validation. What you see on the left is a scissor jack. Imagine a scissor jack which is supposed to lift a payload of 3 tons. The superstructure weighs 1.2 tons. The structure below the top frame weighs 1.9 tons. So 3.1 tons is the total structure. The payload is 3 tons. If you reduce the overall structure weight, then the scissor arms become slender. The power packs required become smaller. The bearings selected becomes smaller. The actuating forces are reduced. The hydraulic power packs oil consumption requirement is reduced. The pump that is required is smaller. The power consumed by that is smaller. The overall reaction time for the scissor to lift up and come down is higher. The response is better. And now the overall cost can be seen to be coming down. Will the deflections be under control? How much material can I save? On the right side, lower, you see a gantry crane sitting over there. A 60-ton gantry crane lifting a payload of 110 tons with a span of 13 meters, 28 meters, and a lift of 13 meters got reduced by more than 10% in one single design validation using SolidWorks simulation. Can I get the load distribution coming in there? Do I have acceptable weld strength and critical locations? Where are the critical locations? What is the maximum load the structure can withstand? Where should I perform the non-destructive testing in the critical areas? Which are those critical areas where NDT needs to be performed? Will there be vibrations during operation? How to meet the price reduction targets? These are questions that are asked by material handling equipment designers day in and day out to stay profitable. Medical equipment design validation. This is really a must considering the safety and the patient requirements. Will my medical device work without any stoppage, specifically when it is in the operating theater? How reliable is my product? How repeatable are its functions? Where are the failure modes? What are the things that can go wrong? Will the surgeons be able to handle it without any issues or problems? How to keep our development costs low? Can I avoid a product recall? Is my device safe for usage? What is the technological edge I have over my competition? Unique selling points. There are many more questions, especially with regard to the medical equipments, that need to be answered, and design validation becomes mandatory as a part of the process here. Pump design validation. Agricultural pumps, industrial pumps, which need to work 24/7. Specifically, coolant water pumps in large factories, in power plants, in process equipment industries, in process industry. How efficient are these pumps? How green are these pumps? Can power consumption be reduced for the same flow characteristics? Can we reduce the product cost? What is the mean time between failure for my pump? How can I eliminate the vibration problems, the cavitation problems? How can I ensure that the bearings and the seals do not fail? How do I extend the warranty without any cost penalty attached to it? Critical requirements in pump design validation, if this is mandatory for the health of the pump industry. Mechanism design validation. Complex mechanisms designers set forth to bring about to handle the statement of requirements for certain kinds of designs which require innovative thinking. Will my design work? The mechanisms, you don't need to do a prototype to make sure that they look at it in motion simulation, and you are able to see whether the components are going to engage with each other the way the designer intended and the design works or not. What would be the response time? How efficient is the design? Can I optimize my design for the least power? Is it possible to obtain required response time? Imagine a switchgear unit, which is supposed to be like a switch breaker, an electric circuit breaker, having the least response time and the maximum response time. It is the difference between life and death. Where would it fail? What is the mean time between failures again here? Can I make my design cost effective, specifically with regard to my product's acceptability in the marketplace? Finally, we come to the corporate social responsibility, which is taking more ground these days as compared to what it was earlier. Sustainable designs, green designs. Sustainability, touching lives. Will anyone buy a pump that consumes more energy? Buy an air conditioner that draws more current? Live next door to a garbage disposal center? Buy a washing machine that consumes more water? Drive a noisy car? Buy a mobile with talk time that is less between power recharge? In all these cases, sustainable designs are touching our lives. Regulatory angle comes into focus. Eco-friendly labeling of products is mandatory these days. Initially applicable to refrigerators, air conditioners, distribution transformers, fluorescent lamps, and other energy-consuming devices. Now on electric motors, the color televisions, the liquefied petroleum gas stoves, they have to carry the mandatory labeling. So sustainability becomes a norm more than a choice. The ISO 14001-2004 specifies the Environmental Management Systems guidelines to identify and control the environmental impact of its activities, products, or services, improve its environmental performance continually, implement a systematic approach to setting environmental objectives and targets, to achieving these and to demonstrating that they have been achieved. SolidWorks sustainability helps us in getting the carbon footprint, the energy consumed, the air acidification, and the water eutrophication. These are the environmental impact assessment indicators that are provided for the design upfront. What are really the implementation considerations for this? Minimum material use, improved material choices, design for ease of disassembly, product reuse or recycling at the end of life, minimal energy consumption, manufacture without producing hazardous waste, use of clean technologies as a fundamental mindset. This is exactly what SolidWorks sustainability emphasizes and helps customers achieve. Now, sustainability and bottom line profitability. Where is the question of sustainability if my business is not profitable? Let's take a look at that argument. The goal is least amount of material. It leads to reduced cost. Least amount of energy. Again, a reduced cost. Least amount of resources being used. Again, a reduced cost. Eco-friendly. Increased value for the customer and a unique selling point for the customer. How the customer perceives it. Smallest carbon footprint. Incalculable value. These are nothing but the recipes for success, specifically integrating the sustainability as a part of the design process. So, design validation enables us to innovate, improvise, indigenize, improve the profitability, give the best to our customers, be the best corporate citizens, leave a greener earth for future generations. This presentation has been brought to you with the software products SolidWorks, SolidWorks Simulation Premium, SolidWorks Simulation Professional, SolidWorks Motion Simulation, Flow Simulation, and SolidWorks Sustainability. We hope you enjoyed this presentation. If you liked this video, we request you to give us a like. Drop your comment so that we can get better in our presentations of the future. And if you need us to help you in delivering on design validation requirements, please do let us know on info@egs.co.in or visit us at egs.co.in or egsindia.com. Thank you and have a good day.